Okay, so here's a formalized version. Probably what I should have started off with you, not to confuse you so much. So that other problem I just wanted to reference because it's not going to get any harder than that. This is on page 125. And here's your second derivative test formalized. So as long as your graph's continuous, if your first derivative is 0 and your second derivative is positive, then you're going to have a local minimum. Conversely, if your first derivative is 0 and at that same value plug it into the second derivative and it's negative, meaning less than 0, then you're going to have a local max. All right? Remember from the last video, if both the first and second derivatives are 0, inconclusive. However, it will tell you points of interest because if you can find when it is equal to 0, sometimes the concavity will change and it'll be an indicator for a point of inflection. So you really got three things going here. You got the first derivative test, which just tells you if the slope's positive or negative. The second derivative tells you what's happening to the slope of the tangent line. In other words, how your first derivative is changing. If it's getting more positive, less negative to more positive, such as something like this, you'd have something that's concave up. If your slope, notice I'm just imagining a parabola here. Am I going from positive to less positive to negative to more negative? Then you're gonna have something, your value will be negative for your second derivative, meaning you have a concave down scenario. So let's take a look at this. I'll bring the notes over here. So here's the same function. And the first thing of example 3 says, find the intervals of concavity and the inflection points. So first thing to do is set that puppy equal to 0, or excuse me, the first derivative equal to 0. So if I took the first derivative, and that was 12x squared plus, go ahead and sneeze. My niece has to sneeze. So there's my first derivative. And if I set it equal to 0, 12x squared plus 6x minus 6, divide everything by 12. Oops, I'm sorry, let's do 6. She's laughing at me because I'm goofing up here. That's going to be 2x squared.
I said set that puppy equal to 0.
Yeah. She's having a good time. And then, again, factor that out if you can. I know I'm drawing over my graph here, but that's 2x and an x, and that's going to be a -1 and a +1. So those are my factors, or my values, my critical points. I've cheated. I've gone ahead and done the problem kind of already. But what's going to end up happening if I set 2x minus 1 equal to 0, x is going to equal 1/2. And I'll do the other one down here. If I set the other value, so that's finding where my critical points are. So there's a possible critical point. And if I set x plus 1 equal to 0, x will equal -1. So there's my other possible critical point. You should be getting real good at finding critical points on your graph. And notice what I'll do at -1 and at 1/2. Instead of that chart, what I end up doing, now we're going to graph this thing blind, I portion off and segment my graph. And a lot of times I'll just say, hey, I have a critical point here and a critical point here, somewhere on these values. Now I've gone ahead and plugged in -1 to my original function to figure out where it lies, kind of at 6. You can do that if you want, or you can just kind of eyeball it. Same thing with 1/2. My y value will be -0.75. Again, I just plugged in 0.5 into my original function. You're gonna have to trust me on that. But so I have critical points, and something interesting is happening in between here, before here, and afterwards. So that's really what you're gonna test. Now, using your first derivative, which we did and have been doing the whole time, you could use the first derivative to look at slopes. But the whole reason to start introducing, Miley, just a second. I'm making a video. That's my daughter. The whole point to use the second derivative is so you can check for concavity. Now, if I take the second derivative of this function, 12x squared plus 6x minus 6, that's going to end up being 24x plus 6. And I apologize to you guys at home because my kids are not listening. If you set that thing well, don't even set it equal to 0, I'm sorry, but this is your second derivative, and I'm sorry for how messy this looks. But remember, the second derivative test, you can test your critical points in there and see what happens. So I can plug a -1 in to see what the concavity is. And if I plug in -1 plus 6, what does that equal? -24 plus 6 is, I think, 18. Now notice, it's not positive, but negative. Be careful of this sign, -24, so this is negative. So because it's negative, it's going to be concave down. In other words, here, I'll put concave down at that critical value. So you know your graph is going to look this way. And over at the other critical value, if you plug in 1/2, if I plugged in 24 times 1/2 plus 6, that's going to equal, well, I don't know, what is that? 12 plus 6, or positive 18. Now again, I don't care about the number per se. I care about the value, if it's positive, or in the last example, negative. Because this is positive, it's going to be concave up. So then you know your graph will do something like this in here. All right, so you're already getting it's kind of a general shape of what's going on. My intervals of concavity, though, are in between here, and I don't know where this changes. I know it's going to have to change somewhere in here, but I just don't quite know where. And that's what I was alluding to in the last video, and maybe briefly here. If you take the second derivative and set it equal to 0, so 24, and I'm running out of space here, x plus 6, set it equal to 0. I bring the negative over here, and that's 24x, meaning x will be, now if I divide both sides by 24, that's going to be negative 1/4. At negative 1/4, right in here, I don't know what's going on because the second derivative of 0 doesn't tell me much, but I pretty much bet you that that's going to be a point of inflection. All right, now I've done everything from example 3 on this separate piece of paper over here, but if you wanted to find intervals of concavity, if you were to plug in any value less than negative 1/4, you already know it's concave down. So I'm concave down until this value here. I'm concave up until this value here. So what you can do, if you wanted intervals of concavity over here, that negative 1/4 value is very helpful. Remember, we got this by setting the second derivative equal to 0, even though it didn't tell us for sure what was happening. It told us to go look before and after that value. Before it concave down, after it concave up. So you can say concave down, concave up here. And so my interval of concavity is in here. This is up, and over here is down. So over here, that's how you're going to find your inflection point. My interval of concavity will be from -infinity to 1/4. And we'll call that concave up. I'm sorry, concave down. And from 1/4 to infinity, concave up. And because I'm changing from down to up, or vice versa, remember, this point here is an inflection point. Now we did this one blind using the second derivative test. You can at any time use your first derivative test, especially if your second derivative is inconclusive sometimes, or it doesn't exist. Sometimes people will revert back to the first derivative. Do whatever makes sense to you. But over here, to answer example 3, inflection at x equals -1/4. So that's how you'd have to find it. If they're asking me to find local maxes and local minimums, we've already kind of proven it. Because the first derivative, now I'm going back to that original, can you pan over here? If the first derivative is 0 and your second derivative is positive, then you have a local min, and that occurs here. The first derivative was 0 at 1/2 from here. And when I plugged in a half to the second derivative, it was positive. So that by definition had to be concave up. Likewise, the other one, if your derivative is set equal to 0 and you find a critical point there, and then you plug that same c value, for us we're using x, into your second derivative and it's negative, then you have a local max. All that means is I found this critical point. Notice critical point was at -1. I used the first derivative, set it equal to 0, found my possible critical point, critical value, and then I took that same number and plugged it into the second derivative. Because it was negative, that by definition had to be concave down. So concave down at -1/6, and that's going to be a local max, and you can see that from here. So all of this is coming from derivatives, and likewise this is going to be a local min. So over here you can say concave up at 1/2 -0.75, and that's going to be a local minimum. Hope that helps. Keep watching videos. Soon be time to practice.